this section, 7-2, we're going to be talking about water, steam, and ice. And there's a nice picture in your textbook that shows the combination of all the different kinds of things we're going to be talking about. Water, ice, condensing water onto the surface of this little pitcher, boiling water, and steam, and water droplets that are coming out of the steam as evaporated water. So we'll be talking in essence about phases of matter, at least to start with. And as a quick reminder, and you already know, there's three essential states of matter: solid, liquid, and gas. The difference between them is that solid is incompressible. Like if you have a brick of gold or something like that, it's not going to alter its shape very easily. But liquid, although it too is incompressible, I mean, if you had a surface or a cubic container of water, and let's say you had it in this cube and you put a cover on it, and then you tried to push down on the cover of the water. Well, guess what? Even though water can squish, it can't in other words, it can come out very easily of the container. But if you had that very tight, so you were just pressing straight down on the water itself, it would, just like solid, it would be incompressible. You can't push and squeeze it very easily, although you can alter its shape. The difference between all of these things is gas is compressible. In other words, I could put gas in a nice cubic container, and it's pretty easy to squeeze down on that gas. If I had like a piston, push down on the gas, and then the gas molecules would just be made so that they were a little more compressed in that container. But we couldn't do that with liquid because it's so close together already that it's really hard to do. And of course, solid is in its little crystalline structure. So we've got our phases of matter, and I'd like to begin with a little bit of a clip that shows you in a nice way how ice, the solid, can melt and become liquid. So melting, again, is just a phase transition. So let's go back up. We're going to look at this. Okay, so this is water, or liquid water, right here. And melting is, if we change this into solid, and we're going to cool it down so you can see how it is not, it's not vibrating quite as much as I take heat out of it. And what happens when it begins melting is a transformation from that ordered solid phase to a disordered liquid phase. This transition occurs when the heat breaks down some of the chemical bonds between water molecules and permits those molecules to move past one another. So melting transforms ice into water, and it loses its rigid shape of the crystalline structure. Now we know that 0 degrees Celsius is ice's melting temperature. That's where the phase change happens, right? Between solid and liquid. Ice doesn't just, if you have ice and you start warming it up, you add heat, it doesn't just keep getting warmer and warmer and staying as ice. All of a sudden there's this phase change at 0 degrees Celsius, at least at normal atmospheric pressure. So what will happen is we will add heat, and as soon as all of the ice becomes water, it will change temperature. So what do I mean by that? Let's watch this. Okay, we know 0 degrees C, it's ice, right? Okay, so we have an ice cube. Now, what we do is we add in 333,000 joules for 1 kilogram of water. 1 kilogram. We add all of that energy in, and it changes this block of ice into water, right? But guess what? That whole time it's staying at 0 degrees Celsius. It's not changing temperature, even though you're adding a whole bunch of heat in. Why? What's happening to the heat? It's just breaking all of those chemical bonds, right? And that's, see, here we go. It's tightly structured, sort of, and we change it into liquid and we break all those bonds. So all of that energy is not going into changing the temperature. It's simply going in to breaking the chemical bonds. So it turns out for us to warm water up, if it's already water and we want to warm it up by 1 degree Celsius, then all we have to do is add in 4,190 joules, and we can warm up a block of water by 1 degree Celsius or 1 degree Kelvin. So if it's already water, it's a simple matter to warm up. But to get it to be water in the first place, we have to add a whole great big wad of energy. This energy is called the latent heat of melting. Turns out that, of course, that's what we put into it if we wanted it to melt, but that's also what we'd take out of it if we wanted it to freeze. Same quantity, just one is the latent heat of melting, that's to make it melt, and the other would be the latent heat of fusion if we wanted it to fuse or become ice. Now it turns out that if we added that much, if our block of ice had just been turned into water, so we'd added this much, and then we started to warm it up by adding this much energy again, that actually would take the water all the way from 0 degrees C to 80 degrees C. That's how much power, or rather energy, we would and how much it increases in temperature. So it's an amazing, water can hold a lot of energy, but it takes a lot of energy even to first get it to become water instead of ice. Next, let's look at boiling water. Okay, when you have water and it's boiling, what that is an accelerated form of evaporation. So when you watch, if you watch boiling water, what will happen is little bubbles will start to form. At the very beginning, a little bubble will form. It'll kind of start to go up. Inside that bubble, let's look at an enlargement of that. Inside that bubble is water vapor. It's not air, it's water vapor. And as it begins to, so this is in response to the heat we're adding, right? We've got heat here coming in, and we get these little bubbles of form of water vapor. Now, as the water vapor is lighter, right? So it rises up. As it rises up, the water that's surrounding it is cooler. And so within that water bubble, as it's going up, these water molecules will condense back onto the surface of the bubble. So the bubble will, in essence, collapse. But as we add more and more heat, we'll get bigger and bigger bubbles, water vapor bubbles. And they'll actually go all the way up to the surface and then kind of erupt onto the surface, and water vapor will go off, more water vapor. So as the water begins boiling, we've got all of these water vapor bubbles are coming up, and they're releasing their vapor onto the surface, and it goes off. So we've got heat energy going in, big heat energy, and we've got heat energy being carried off by the water vapor. So what does that all mean? Once the water gets up, we heat it up to 100 degrees C. It will not get, the water itself will not get any hotter. Instead, the heat is carried off by these evaporating water molecules. The water itself remains at 100 degrees C. So remember, that's how a rice cooker can tell when the water, or when the rice is done, because all the water will have kind of gone down until all the water is evaporated. As soon as it's evaporated, then the surface of this metal will get hotter than 100 degrees C. We've got a little temperature detector there, and that goes off when it starts to rise above 100 degrees C, and then our rice cooker naturally turns off. Now what happens if we have something like a pressure cooker? Okay, we've got a pressure cooker. Here's my beloved pressure cooker. And we've got a nice tight lid on it, right? And so we add our heat, and we've got water inside, and as we're adding heat, it's going in, and what will happen is these the water begins to form these water vapor pockets, right? And they go up to the surface. But guess what? When it gets up to the surface and it starts to evaporate, it can't go away into the air like it did here with this open boiling pot. So what happens is the water molecules leap into the vapor, and more vapor forms in this closed pressure cooker. So actually, this goes higher than atmospheric pressure. In fact, it goes up, I believe a standard pressure cooker goes up to about 2 atmospheres. So high pressure in here, right, as this begins to boil. And what they have is they've got like a little hole usually right there, and then the old-fashioned kind, at least, they had like a weight that they would put over the hole, and this weight would kind of bobble back and forth and allow some steam to come out, enough so that it wouldn't get to super high pressures and then so high that it breaks the pot. Actually, the development of steam pressure containers, that was, for a long time, it was considered very well, it was very dangerous, because if you had these big pressure boilers, as we saw in that movie, the Sand Pebbles, then if something happened to them and they exploded, if there was a crack in one of the boilers, it could kill a lot of people. So there were a lot of design issues in ensuring that containers that are supposed to be pressurized don't break. And today's pressure cookers indeed are really quite a safe set of contraptions. You can imagine in today's litigious American society, they have to have a great deal of attention to the design. So what happens now is, as a certain amount of steam develops in here, when the steam pressure gets high enough, it's able to escape out the edges. And there's also gaskets that can release in case pressure gets too high. But what I really want to get to is the idea that at 2 atmospheres of pressure, what happens is the water is boiling at 2 atmospheres of pressure. So it's boiling in there, but it's boiling at about 125 degrees C instead of 100 degrees C. Why is that? Because the pressure that builds up, this steam that builds in this area, pushes back. So it's harder for water molecules to leap off the surface. So it doesn't boil until it gets hotter. It actually can get above 100 degrees C, which is not the usual case at normal atmospheric pressures. It's this pressurized container that allows it to boil at a higher pressure, or a higher temperature. Higher temperature means that the food cooks faster. So that's why a pressure cooker, you might be able to cook a load of beans that would normally take 3 hours, you might be able to cook in 1 hour. Maybe a third of the time is the cooking time that you would use with a pressure cooker on average. Now, another interesting phenomenon is when you might have a cup of, let's say that you're making a cup of tea. I love tea. And when you put it in a microwave, if you have a nice clean cup and you put water in there, what can happen is the radiation comes into the cup, and what it's doing, what that microwave radiation is doing, remember that water molecules have an O here and H's here, and this is a little bit more negative and this is a little bit more positive. So it's like you have something that's a positive and a negative, like a dipole. And so as those electromagnetic waves come by, walk past or run past, they're running very fast at the speed of light, as they go by the water molecules, they actually swivel them. These plus and minus on the dipole serve as handles. So it might go like this and then swivel back, right? So first it'd be this way and then it'd be this way, and it's just your water molecule is going to swivel back and forth because of the alternating electromagnetic waves. So you're heating it up by friction, just making these water molecules wobble back and forth. They heat up, heat up, heat up, but your water doesn't seem to be boiling. And you can, if you're not careful, you can reach in, grab a cup of coffee or a cup of something from the microwave. All of a sudden, it will spew water all over the place as steam. Why is that? It turns out that boiling takes place oftentimes because you need a first little tiny pocket of something, just something that the water, the steam can nucleate around and form a larger bubble with. If you have a rough cup, turns out that will allow more nucleation sites. You have a very smooth, very clean cup, not very many nucleation sites. So your water, as it turns out, can get up to like 102 or 103 degrees Celsius. That's above boiling. So now you go in, you plop your tea bag in, right, like I do, plop it in the water, and whoa, all of a sudden you've just given it a bunch of nucleation sites and it explodes outwards. Likewise, you can pour chocolate powder into the water if you're making a cocoa mix or something like that, and it'll explode outwards. So you always have to be careful with this kind of thing, because you can superheat the water if you're not careful. And the last idea is simply that if you have a dissolved chemical in water, so let's say here's your driveway, you've got some salt that you put on the driveway, and then the snow comes down, you put a little more salt on. Well, actually, that salt or any kind of chemical can entangle the water molecules or entangle the ice, so that the water is less likely to have a phase transition. So if you have water that's got salt in it or sugar in it, it will boil at a higher temperature, or it'll freeze at a lower temperature because it's entangled. And you've got sort of something else within the water that makes it so that it's more complicated, and it has to take more energy in order to melt. Now let's look at another phase transition, that between water when it evaporates and condensing steam. So now what we're going to do is look at the surface. This is water, and you can see it's a little bit easier on water. It's a little bit easier sometimes for these molecules to leap the bonds of the surface of the water, and also sometimes they'll come back. So in other words, water's open surface is another active interface between the phases, but this time the liquid water is exchanging molecules with the gaseous steam. So water molecules are feverishly leaving the water for the steam, and they land on the water from the steam once again, kind of like planes at a busy airport. Well, there they go, off and coming back. So evaporation, let's write this down. Evaporation is the phase transition from liquid to gas. And condensation, on the other hand, condensation is the phase transition from gas to liquid. So as you can see again here, we're bringing this back here. Although the bonds between the water molecules are weaker than the bonds between the bonds between those water molecules they're weaker than the ones that actually hold the molecules themselves together. In other words, like the hydrogen and the oxygen are tightly held together, but the ones between two water molecules are weaker. But even so, it still takes a great deal of energy to transform that water into steam. And what that energy is called the latent heat of vaporization. As opposed to the latent heat of melting. So we're not just melting an ice block, we're actually vaporizing water, and it's enormous. Because these water molecules, even though they're loosely bonded with one another, not at all as strong as the bonds within that molecule, but they're kind of bonded with one another. And so what it takes is, and get this, 2,300,000 joules of heat. energy is needed to convert 1 kilogram of water at 100 degrees C into 1 kilogram of steam at 100 degrees C. Look at that. You can have this water, like a chunk of water here, and you put a whole bunch of heat into it. You put all of this heat in, 2,300,000 joules of heat. I'm going to put Q because that's what we usually use to represent heat flowing in. All of that heat, all it does, it doesn't change the temperature at all. It just changes its phase from liquid to. Now, in the same way, if we wanted to think about, let's see, our skin. So let's say that this is the surface of my skin. I've got water, a bead of sweat. A water molecule jumps off the skin. Well, evaporation off the skin can lower your temperature at that place by around 15 degrees Fahrenheit. A lot. So now, what is relative humidity? Relative humidity is basically the landing rate of a water molecule over the leaving rate. So if this is low, if you have low relative humidity, then that means that very few molecules land on a surface. So very few of them come and land on your skin, for example. But a lot of them will leave. So more of them want to leave, and few of them want to come in. That's what low relative humidity. High relative humidity, you've got more coming in, right? And fewer of them leaving. That would be high relative humidity. So if the relative humidity is more than 100%, the landing rate is more than the leaving rate, and steam condenses. So that's just what we saw here at the very beginning in this first drawing. You have droplets of condensation. Why? You have more water molecules landing on the surface than you have leaving the surface. Why? Well, this is cold, and so water molecules come in, but they don't have enough energy to leap back off. So that can be why steam condenses. Now, if you have rising temperatures, what they do, rising temperatures favor evaporation. Yeah, that makes sense. You put heat into something, and it gives those water molecules on the surface of anything more of an ability to leap off. So when the relative humidity is low, on the other hand, then water can evaporate very quickly, and the air feels very dry. So perspiration can cool you very effectively in those kinds of situations, because the water can take off, they can evaporate. So when we have high relative humidity, so near 100%, the water will barely evaporate at all, right? So here's a glob of water on your skin, and it can't get out because there's already enough by way of water molecules in the air that it's difficult for these water molecules to jump out into the air. So the air feels damp, perspiration clings to your skin, and it doesn't cool you very much. So it just feels very muggy. In the Sahara Desert, or the Arabian deserts, the relative humidity is around 20 to 25%. At the South Pole Station, South Pole, relative humidity was around 2%. Really, really dry. So what that means is your nose dries out really badly. And then for optimal humidity, we would like to have something around 45%. That's nice, optimal. On a high plane flight, you'll have something like 1%. So if you're going up high in a plane, it's very dry. And so that's why they urge you to try and drink at least a cup of water every hour, and then try to avoid alcohol as well on planes, because between the plane flight itself and the very dry air, which dehydrates you, and then alcohol can dehydrate you even further. And so between all of that, you really want to make sure that you drink lots of water and avoid alcohol on planes. Now, I was poking around to try and find the place that has the highest relative humidity. And at least in the U.S., the highest relative humidity is at a place called St. Paul on the Pribilof Islands. That's right off the coast of Alaska here. And as it turns out, I've actually been here to the Pribilof Islands. We were working out our trawler, our Soviet trawler, had to offload, and so we went close in to St. Paul, and we went over onto the island, and as it turned out, this was the last day of the seal harvesting festival. And so you can see, this is a picture I took of there's the carcasses of the seals. And that particular day, since it's the last day of the seal harvest, is a big festival. And what they do is the children will find any outsider or anyone they can catch, and they like to hurl portions of seals at whoever they can find who's unaware of what's going on. So you can be running around here, and if you're in the wrong place in front of a small child, you can find yourself on the wrong end of a seal eyeball. But anyway, this is what it looks like there on the Pribilof Islands on St. George or St. Paul. And anyway, that place has a very high relative humidity annual of 83%, which is pretty high. And as it turns out, this is the place, and in part it's because of this high relative humidity. But in the 1700s, the Russians were coming over here, and they were looking for seal pelts. The fur seals were an enormously valuable resource. And so they were harvesting fur seals, and they were trying to find out, where did the fur seals breed? As it turns out, they finally homed in and found them on the Pribilof Islands. That's where the fur seals prefer to go to breed because, well, it's high relative humidity, it's isolated. And I still remember landing when we went ashore on these little boats called Zodiacs, and I remember looking all around me. There was a heavy mist in the air. You can see the mist that day, and the surface of the water was pressed absolutely flat. But when we looked around in our boat, you kind of felt like there were eyes around you all the time. And when you looked very carefully, you could see, indeed, there were eyes, because there were seals poking their little noses up above the water. So in our boat, we'd be seeing all these little fur seals peeking up at us. It was really quite an experience. I highly recommend going to the Pribilof Islands if you just want to experience a place unique, even though you can experience 83% humidity and above fairly commonly at any random place in the United States. It's just that this is the highest overall on average within the U.S., according to statistics at least. Okay, so let's talk about some other important points. First, we'll talk about subliming ice and depositing steam. I love that word, sublime. Usually means something that's just extraordinary, but it also means when ice goes directly to steam. That is called sublimation. Sublimation. And in Antarctica, as it turns out, sublimation is important for the collection of something very interesting. I'm going to try and show you. Okay, here's the Antarctic continent in cross section. So down below here, there's the land. This is the ice. Here's this. Uh-oh, I hope you don't hear my granddaughter in the distance. Okay, there's the South Pole Station, right? South Pole Station. Here's your ice. And there's these big mountains that actually rise up. Remember, there's 2 miles from South Pole down underneath to the actual ground itself. And there's a mountain, so these are thousands of miles right here to go over to these mountain ridges. They form deep under the earth, and the ice, what happens is, as snow comes down, the ice comes over here, right? So it's building up, and it's flowing. And it flows, and it hits these under ice mountains, right? That only the tips of their ridges show up here. So it hits, and then it flows, turns, and flows down towards the sea. So as it's flowing over thousands, the ice is flowing over thousands of miles, hits these ridges, gets a real kind of a thin layer right along these ridges, which, there can be hundreds and hundreds of miles of these ridges. What happens is meteorites that have fallen on all this great expanse get carried over to the edge, and then as the ice sublimes, remember there's all this radiant energy that comes down, hits the ice, so every once in a while one of those ice molecules will pop up into the air. So here we go, there's our ice, and it doesn't show it very well here, but you can see every great once in a while, if I sat here long enough, one of these molecules would have just enough energy to rip free and float off as vapor, even though the rest of it is all solid. That's sublimation. So that's what happens. The ice carries these meteorites over to the edge, and then it's able to sublime off the edge of the mountains, and leaves meteorites on these ridges. And so some of these, right along the edge of some of these ridges in Antarctica, is the best place in the world to collect meteorites. They're all kind of clumped along there. Now, of course, it can go the other way as well. We can have steam that goes directly down and deposits onto ice, and that would be like the frost that you see on a window. We call that deposition. Now, at 100% relative humidity, ice and steam are in phase equilibrium. Okay, so also when the relative humidity is below 100%, then ice will sublime, right? Because there's not enough water vapor in the air, or there's not very much, and so it's easier for the water vapor molecule to leap off the edge of the ice and sublime. This is why in a frostless refrigerator you can have ice cubes that shrink, and also why you get freezer burn. Sublimation, as it turns out, which is having these water molecules leap off the ice, is used to prepare freeze-dried foods. So my father worked on the astronauts' food back in the 1960s, and one of the first things he worked on was sublimation of foods, and he used to bring home all these freeze-dried ice cream and things like that for us kids, and we were among the first in the world to ever try freeze-dried ice cream, which was actually pretty good, but there's other stuff, trust me, that was not so good.